Welcome back. The topic today is actually a continuation of what we did yesterday, but I wanted to go a little bit back and repeat some of the examples, because these are things which sometimes it takes time to connect the dots. And there's a reason why I want to do this, is because the different expectation values which we calculated, and also the transition matrix elements, these are things which we will need when we meet our first many-body methods, which is called full configuration interaction theory. So I'm going to set up some of these equations again, and then we are going to use that to prepare ourselves for our first encounter with many-body physics, which is in configuration interaction theory. So we're going to set up a Hamiltonian matrix, and then we will need the matrix elements which we calculated yesterday, and other ones as well. And the idea is to use these kind of things which we are doing now in the first midterm. And the kind of loose idea is to use this Lipkin model, which we have in the exercises. And we have been preparing the ground for setting up this Lipkin model so you can diagonalize it easily. But in the midterm, I was thinking also of not transforming it into these quasi-spin operators, but keep the second quantization formalism, and then use the machinery we set up here to define a Hamiltonian matrix, which we can diagonalize. Then the other thing we will do with this Lipkin model is to perform a Hartree-Fock or a mean field calculation. And the Lipkin model is nice in this sense that it provides us with systems which are easy to diagonalize, and we have also analytical answers for the Hartree-Fock equations. And that's something which allows us, hopefully, to get a deeper insight about the different methods. That's the kind of rationale behind a lot of the machinery which we are setting up now. So I'm also going to link the expressions which we went through yesterday with this exercise which we have this week, and which will also be part of the first midterm. Now, feel free to come with suggestions for alternatives. I'm always open to that. I have a kind of, how to say, not an obsession, but I like to teach so that we tailor things to people's interests. That's always been one of my hobby horses when I've been teaching. But I wanted to repeat some of the things which we did yesterday, and perhaps even go through some of the derivations again so that you see it again. I'm going to postpone the diagrammatic representation of the particle Hall formalism to next week, but I wanted to prepare the ground for full configuration interaction theory, so we can discuss that fully next week. Okay, so then we need these technicalities, and let me quickly remind you of some of the basic definitions which we had yesterday. So this is a quick reminder of where we were yesterday. So we have this general creation and annihilation operators which now act on a vacuum which is different from the true vacuum. And we saw that this could be equal to delta PQ as before, if this P and Q are larger than the Fermi level. So I'm going to use this notation consistently throughout the semester. And then we have AP, AQ, dagger, and this is also delta PQ if P and Q are both below the Fermi level. And then we define the states, like this state phi of I, which is the same as A of I. And this is different, acting on the new reference vacuum. And this is different from 0 if I is an element in the new reference state which we have defined. And then we have an example like a phi of A, which is then given by an A dagger acting on phi 0. And that is if A is not an element in this phi 0. So we are creating a state above the Fermi level. And then it's different from 0. So these equations apply to the case when they're different from 0. So this is an n plus 1 state, whereas this one is an n minus 1 state. So we remove one particle or we add one particle. And then we have the notation which we are going to look at today in more detail. And this is a so-called one particle, one hole state. And this is also different from zero if A is not included in phi 0 and I is in phi 0. If I is not in phi 0, then this is obviously 0. But by the way we have defined these A's and I's and so on, is implicitly assumed that I is an element of phi 0 and A is not an element. So particle states are by definition not elements. Then the last case, then we can make it more complicated. So this is an n particle state, and we normally call this a one particle, one hole excitation. This is a two particle, two hole excitation, and that was given by an A dagger, A B dagger, AJ, and AI. Let me just do it properly here. Acting on the new vacuum state. So these were some of the definitions, and then I just wanted to bring back the definition of the Hamiltonian when we redefined it with respect to the new vacuum state. So the Hamiltonian which we redefined, we wrote that in terms of a term V of n, and then we had a term F of n, which is the one-body operator, and then we had the reference energy. So I just wanted to repeat some of these terms. And this contains a factor 1/4 if we are dealing with anti-symmetrized matrix elements. If we don't have anti-symmetrized, it has to have a factor 1/2, 1/2. And we are summing freely over these states here. Computationally, this is not often the most efficient way of doing that. So this integral which we have here with the AS sign means that this is an anti-symmetrized matrix element which contains a direct term and the exchange term. So this is now the set of normal ordered operators. So when this acts on the vacuum state, it has an annihilation operator acting on the vacuum state. And then when we take a vacuum to vacuum expectation value, this quantity is actually going to give us 0. So if I take the vacuum to vacuum expectation value, because the vacuum to vacuum expectation value is contained in this term here. So this term which you see here, if I were to take the vacuum to vacuum expectation value of that, this is the same as the definition of the creation and annihilation operators, which we applied on the true vacuum. Because this is now a normal ordered operator, and then we have a destruction operator acting on the vacuum state, and then we are going to the vacuum state, but we are not creating it back again. So this acting on the vacuum state produces normally either one particle, one hole, or two particle, two hole excitation. And then we have the next term, which is this one body term. And that term is given by the sum of a P and Q. And then we have this specific operator, which I'm going to redefine. And then I have the normal ordered operators, AP dagger, AQ. So this would be just an example of a general type of operator which we can have. And these integrals which we have are given by the integral which we've seen before for the one body operator, which contains kinetic energy and eventually an external potential, which the particles are confined to move in. It could just contain kinetic energy only. And then we have Q, and then we have this additional term where we modify the motion of a particle due to the states below the Fermi level. So it means that this state or particle moving in the state P sees the medium. When I say the medium, it sees all the other particles which define the system. No, sorry, not that way, but it should be Q of I anti-symmetrized. So that's that part. And then the final piece which we have, this E reference, that is actually our vacuum to vacuum expectation value of the original Hamiltonian which we have. And in our case, this is just a constant. which then contains the sum over all the non-interacting single particle energies, plus this 1/2, and then I have a sum ij, and then it's ij v ij anti-symmetrized. So this is the vacuum to vacuum expectation value, and this is something which we now don't need to calculate again. Now, one of the things which I wanted to remind you quickly about was some of the results which we obtained yesterday. And when you look at some of these expectation values or transition probabilities, some of these are things which you can almost see on the fly what you should get. And the reason why I wanted to repeat it is that because sometimes you don't need to run calculations in order to decide whether this contribution should be zero or not. If you see that it should be non-zero, then you have to run through the calculation. But there are some contributions which you, when you develop some intuition about what you're doing, you can actually say this specific contribution has to be zero. Now, one of the matrix elements which we are going to see again and again, so the examples which we went through yesterday, so one of them is the transition between the ground state, or this ansatz for the ground state, and a one particle, one hole state. And what we found yesterday, when we looked at these expressions, if we now broke it down in terms of phi 0, and then we had the v of n and phi I a, and then plus phi 0, and then we have the f of n operator, and then this phi I a. And then we know that since these reference energies are constant, and we have assumed that phi 0 plus phi multiplied with phi of a, and then we have the E0 reference, so this is just a constant, and this overlap is equal to 0. So E0 ref does not contribute to that term. So that's the something which we can actually set up immediately due to the way we have defined these basis states. And we are assuming that these states, this is a general assumption, that they are orthogonal. If they are not, then clearly this may not be equal to 0. And then we would have to calculate some overlap integral. So that could be the case, because sometimes it can be convenient in many body physics to use a basis which is non-orthogonal. Just to give you an example why you could use that, if you think of systems in atomic physics and molecular physics, it has been common to use the hydrogen type of orbitals as a basis state. Now, the problem with that basis, besides the fact that it's an orthogonal basis is not the problem, but the problem is that these states are always bound. If you think of the single particle energy, it is minus 13.6 divided by this n, the number of nodes which you have in a wave function squared. And that number will always be negative. So you will have an infinity of negative energy states, which we then label as bound states. So that means that if you would like to use the hydrogen basis to describe states in the continuum, then this would not be a very good basis. And in atomic and molecular physics, and some of you may have seen that, it's common to use what's called a Gaussian basis. So you would expand your wave function in terms of Gaussians. But that basis is in principle not orthogonal. You can orthogonalize, but that means that when you calculate some of these overlaps here, you have to be careful. So using a non-orthogonal basis comes with a price. Here, we will limit ourselves to basis sets, a computational basis, which is orthogonal. But just keep that in mind, because you may see that this is not equal to 0. And it is the case when you have specific basis sets which are not physically relevant. They are useful, but they may not be relevant for the specific physics case. Especially if you want to describe states which are bound and states which are in a particle continuum. That was a small digression, but it's useful to think of these things. Now, if we then go back and look at the expressions which we had, if we now take the V of n term I'm just repeating a little bit of what we did yesterday. So the V of n term will now have, since we are doing the transition from phi 0 to a one particle, one whole state to phi 0, what we have here in this case is the evaluation of this term, AQ, AS, AR, and this is a normal ordered operator. And then we have another normal ordered operator, and then we have an A dagger, AI. And these guys are acting on the ground state. Now, one way to reason here is to say that, okay, this produces now, when it acts on this one, it produces a one particle, one whole state. Now, a two-body operator, since we cannot perform the contractions within the operator, so we cannot do that and that, because this is a normal order set, and we can only do contractions between the operators. That means that when we now contract here, we would have contractions of this type here, which is valid. Alternatively, we could have this one that would just give us a minus sign because we would interchange these two guys. So these two guys, one of these has to contract with that one because the contraction here to here gives a 0. That means that the two operators, the equation operators here, have to interact with either here or we have this one. That leaves us, when we now do the contractions here, so suppose we take this one, this is a valid contraction, that leaves us with these two here, which cannot be contracted. This is a normal ordered set, and this normal ordered set, AP, dagger, and AS acting on the vacuum state, you could think of that creating a one particle whole state again. That's the only possibility you can have. So if you go back to the old formalism, if you now think of these two which have not been contracted, this would be a annihilation operator. So that would create now a one particle, one whole state. But then I'm taking the overlap with a state which has 0 particle, 0 whole excitations. So when you have a two-body operator and a one particle, one whole state, and then you take out the vacuum to vacuum expectation value, the number of excitations don't match. So this is a way you can intuitively look at the expressions, and you will say that I'm starting with this state here. That means that if this operator is acting on this state, it should also give me a one particle, one whole state. But this operator here will produce a two particle, two whole state. And then the overlap between these states is 0 if we have assumed that the orbitals are, or the wave functions are orthogonal to each other. Does that sound reasonable? So you can actually look at this term and say that this has to be 0 without running any calculations, because this creates a two particle, two whole state, and this is a one particle, one whole state. That's one way of simplifying life and the amount of calculations which we need. So the only term which actually survives here is this term which goes like phi 0, and then I have the Fn operator, and then multiplied with this AI state. And the elements which we need to look at then are actually this AP, AQ, and then we have an AI of AA with an AI. Sorry. Okay, in this particular case, there is only one contraction which is possible. And the only contraction which is possible is that Q is a particle state and that P becomes a whole state. That's the only possibility I have. All the other contractions are 0. And that leads to, when we do the calculations, that leads to an expectation value, which looks as follows. So I will have I, and then I have my H0 of A plus this sum over J less than the Fermi level. And then I have my I, J, V, and then I have my A, J anti-symmetrized. And this is something which we loosely call a particle whole excitation, because what we have now is a term here, which is a particle state, and this gives us an excitation to a whole state. So it's normally called a particle whole excitation, what you see here, a particle whole excitation contribution. Now, I mentioned yesterday that this is something which is going to play an important role for us. because the matrix element here is going to be important when we are setting up our Hartree-Fock calculations. So this is relevant for Hartree-Fock theory, which comes after configuration interaction theory, for HF theory, which is going to be our second many-body encounter, and which also forms a kind of kitchen item in many-body physics, because you often try to find an optimal mean field. And instead of having a mean field or field, which is defined by the non-interacting piece, you're now correcting the motion of the particles due to the interaction with all the other particles. And this is going to translate into a set of single particle equations, but where the equations now are coupled because they will depend on this interaction term. Okay, now the other thing which I wanted to discuss a little bit is another matrix element where we spent some time yesterday. So I just wanted to repeat it and show you the kind of technicalities which we end up with. So if you now look at this phi 0, so this is the next example, and H and phi ij, AB. So this is another matrix elements which we will need when we are going to set up the Hamiltonian matrix of diagonal arms. And this matrix element, when we now looked at it yesterday, we had a term with obviously with the reference energy, which has to be 0, because these are two different states. And then the other contribution, which we can immediately determine that it has to be 0, is the one which involves the one-body operator. So if we take the Fn piece, then we have a phi ij of AB. And what this translates into, when we now put in all the expressions which we need, so we have the integral, and then we have F and Q, and then we have phi 0, and then we have the operator AP, AQ, and then we have an A dagger, AB, AJ, AI, this is an I, and phi 0. Now, if you now look at the terms here, you can immediately see that this also has to be 0, because here we create a two-particle two-hole state. So that means that what we have is a two-particle two-hole state, which is being created here. If I now look only at the state which I have here, this is a zero-particle zero-hole state. So this would be zero-particle zero-hole. Now, what you have here is an operator which can at most produce a one-particle one-hole excitation. So that means that when this guy is acting here, you can get a one-particle one-hole excitation. And clearly that will not match a two-particle two-hole excitation if you have assumed that the states are orthogonal. So this is also something which you can see immediately due to the type of excitations which are involved, that this has to be 0. Does that sound reasonable? So you can actually look at what kind of states you create in these different operations, and then you look at the fact that you're doing, at the end, you have a vacuum state here, the new reference state, and a reference state here. And these different operators, they bring you to different types of two-particle, two-hole, one-particle, one-hole, etc. states. And in order for this transition from here to here to match and give something which is non-zero, then the type of excitations you look at, they have to match. So clearly here, the only term which can contribute is the case where you have a two-body operator, because the two-body operator is the one which can take out the two-particle, two-hole excitation and bring you back again. So I'm repeating things which we did yesterday, but the aim is to allow you to see how you can build up an intuition in terms of these particle-hole excitations. So you can, at the end, when you've gone through this many times, you can just look at some specific transition elements and say this has to be 0 by default. And that's the handiness of having redefined the reference state which you have. So the only term which survives here is actually the one which involves the two-body interaction. So when you take this term, and now I'm just going to look at the contractions. So Ij, AB. So this is going to be proportional with, and now we're going to set up the possible contractions. So we're going to have an AP, AQ. I just wanted to repeat this one, although we did it yesterday, but we didn't go through all the details. That's AB, and then AJ, AI. And here we can now set up the possible contractions, and let's try to do that. And you will see that there are only 4 possible ways by which we can find these possible contractions. So what you could think now, when we use this contraction rules, this is a possible contraction. And then we can also have this as a possible contraction. And then Q would go to this state here, and P would go to that state. So in this specific case, we have operators which are just standing by each other. We perform this one, gives a Kronecker delta. This one with that one gives a Kronecker delta. So there is no interchange of lines here. So that means that we don't need to change or permute the operators. So this is just going to give us a plus sign. So we will get, at the end, we will get a matrix element, which is given by, so P and Q are equal to I and J. So I would have then a matrix element, which goes like this. And then I have V, and then I have AB anti-symmetrized. Now, what I'm going to do now is to change the 2 particle contractions, but I keep the 2 holes fixed. So this will be 1. If I take the next one, I'm going to keep the 2 hole lines like that. And then I have this one, so they are the same. But then I'm going to take S to A, and then I'm going to take R to B. Now, in this specific process, what happens is that I have to interchange, I have to permute the operators. So I need to permute A, S, and R. That gives a minus sign. And when I set up the Kronecker deltas now, what I will get is minus due to that interchange of the operators. I get minus 1 divided by 4. I and J are the same positions, but now I have B and A anti-symmetrized. Now, the way I have defined these matrix elements, if you look at this Ij of V of AB anti-symmetrized, these are matrix elements. I just wanted to repeat this. I hope you can excuse me if I keep repeating things. And then I can have an Ij and a V of BA, like that. That's a definition. Now I can obviously, if I interchange A and B, because these are just dummy variables, and then what you see then, you have Ij, V, B of A, anti-symmetrized, and that is the same as Ij, V, B of A, minus Ij of V of AB. And if you look at that one, that is the same. So if I take these 2 guys, this is the same as minus Ij V of AB anti-symmetrized. That makes sense? So that means that I can actually rewrite the term you see here as 1 divided by 4 and Ij V of AB. If I were to use the matrix elements without setting up the anti-symmetrized one, there would be a factor of 1/2. But then I would use the translational invariance of the 2 variables which are involved in the integrals, and I would get actually the same result here. Okay, so the next thing you see now, these are the only contractions which are non-zero. What I could do now is to interchange these 2 guys. And finally, I could now interchange all sets here. So that's going to give rise to 2 more sets of contractions, which give non-zero results. All the other contractions are going to give 0 results. So let's do the final thing here. and take the last ones. So we have AP dagger, AQ, AS, AR, A dagger, AB dagger, and then I have my AJ and AI. So if you go back, what we did now was to interchange these. But what we could do is to take this one and keep that. But now we interchange the two whole lines. And that gives also a minus sign. So when I do the contractions here, this is going to give me minus 1/4. And then I'm going to have JI of V of AB anti-symmetrized. And this is the same as 1 divided by 4 of IJ V of AB anti-symmetrized. And then the final one, I'm just going to write it here. So that's going to be AS to AA, AR to AB. And then I'm going to have AP to AJ and AQ to AI. And that will give me a matrix element, which has now two interchanges. So I get a minus sign from this interchange, and I get a minus sign from this interchange. So that gives me plus. So I have plus 1 divided by 4, but then I'm going to get JI of V of BA anti-symmetrized. And that is the same as 1 divided by 4, IJ V AB anti-symmetrized. If I were to run this without the anti-symmetrized matrix elements, I'm going to get the same result at the end. And the same result at the end, when I collect all these terms, I have 4 equal terms divided by 4. So that means that the only thing which survives when I calculate this specific guy here, phi ij AB, is equal to ij, just a matrix element, AB anti-symmetrized. And this is something which we found from the Condon-Shortley rules. No, the Condon-Slater rules. Where we actually went through the integrals in first quantization, and that was the exercise in week 2. And then we looked at the overlap between, or the transition matrix element between a state which had 2 single particle states which are different, which is actually the case you have here, and with this state here. So what differs here is that you have just made 2 single particle states to be different. And with a 2-body interaction, this is the only term which survives. So we have shown that we can get back the same result as we had previously. Now, the one of the other matrix elements which I wanted to set up, and which I'm going to leave to you guys as a small exercise, because it can be useful to do that, is the matrix elements where I have an IA. So this is a 1 particle, 1 hole to a 1 particle, 1 hole state. So in this specific case, we can now assume that J is different from I, and A is different from B. And we still assume that the states are orthogonal. That means that when I calculate this overlap, for this to be non-zero, it has to be delta Ij multiplied with delta AB. And that's pretty easy to show here, because if we use these second quantization operators, one of the things which we have assumed is that phi 0 to phi 0 is equal to 1. That's a basic assumption we're making here. And then when we now calculate this term here, what we have is that we have this specific operations of AA, and then I have an AB dagger and AJ acting on phi 0. And now you see when you perform the contractions that since these are particle states, the only possibility for this to be non-zero. So we're actually showing the orthogonality of 2 Slater determinants using second quantization. And you see now that this simply leads to delta Ij and delta AB. So if we assume now that these are different, then clearly this has to be 0. That means that when we calculate the expectation values here, and we have the reference energy, which is a constant, then that term is going to be 0 again. That makes sense? So the only thing we need to look at then are actually the expectation values of the one-body operator and the two-body operator. And what you're going to find then when you do these calculations, at least if I did things right here. So what you will get, the final expression, is something like this. So this is what you should get. You will get a matrix element which goes like AJ of V of IB, anti-symmetrized, plus, and then you will have a delta IJ multiplied with A of F of B minus delta AB of J of F and I. Now, since we have assumed that A is different from B and I is different from J, the only term which survives is going to be this term here. So that means that you would have to go through the application of the two-body operator. So this comes from actually the two-body operator. This comes from the one-body operator. And the two-body operator is actually pretty similar. The type of contractions is pretty similar to what we did here with the previous case. So I'm just going to leave you that as an exercise. But the reason why I'm putting emphasis on this is that we are going to use this now, both in the exercises with the Lipkin model and also in the calculation of or the setup of full configuration interaction theory. So just as a small digression, before we take a small break, if we now look at the Lipkin model, which we had in the weekly exercise last week, and also parts of it this week, in this specific model, what we have is n equal to 8 single particle states. And we have n equal to 4 particles. And our system is now set up so that we have an energy level which has 4 possible slots. So we label this 1, 2, 3, 4. And this corresponds to a state with spin down. And then it has additional quantum numbers 1, 2, 3, 4, which we don't specify. They could just be any kind of quantum number we want to use. So these are slots where we can place the particles. And then we have this one with a spin up. And we have these different slots like this. And now if I'm filling them in here, you see now that you can now use these type of rules to set up this as your ansatz for the ground state. This could be your phi 0. And it's a reasonable ansatz because we're going to assume that the energy, the single particle energies here, are below the single particle energies of this state here. So when we add the single particle energies, this will be a quantity which has a lower energy than this one, the single particle energies, before we put in the interaction. So this could be a useful ansatz. And then you clearly see that we can now make 1 particle, 1 hole, 2 particle, 2 hole, but we can make up to 4 particle, 4 hole excitations. And the total number of states which we have, if you do this, so you have a combinatorial number of Slater determinants you can make, is given by 8 of 4. And when you do the combinatorics, this is going to give us 70 possible Slater determinants. In our case, we have 4 particles. That means we can make at most 4 particle, 4 hole excitations. And since the number of single particle states you have is limited to 8, you have a limited amount of excitations. So you have only 70 states which you can make. And one of them is going to be this one. This is unique because there's only one way you can fill it, but you can make many particle hold excitations. There is only one 4 particle, 4 hole excitation, and that's when all these dudes actually are filling in this one. That's the only 4 particle, 4 hole excitation. But we can have many. So of these 70 states which you see, there will be one which is 0 particle, 0 hole. So we are going to call this one for 0 particle, 0 hole. And there's going to be one 4 particle, 4 hole state. So it means that we will have the 4-particle 4-hole state, is now going to be given by this one. If we think of these as particle states, and we define the Fermi level to be here. So this will be now vacated, and we will have excited all the particles to the state above the Fermi level. So we would call this for a 4-particle 4-hole state. And then you see we can make then many different types of excitations, and they will depend on the Hamiltonian. So in this project, which we will have for the midterm, we're actually going to look at the calculations of these different types of matrix elements which we need. And you have the recipe to find the analytical expressions, like we did here, in this specific case, with that element, and the way we did it here for the transition between a 1-particle 1-hole state to a 1-particle 1-hole state. So you have some general expressions which can be used to set up the Hamiltonian matrix. So we could now think of us having a 1-particle 1-hole excitation, 1, 2, 3, 4, and then we promote this one to the state 5, 6, 7, 8. So this would be a 1-particle 1-hole excitation. And then we can have a 2-particle 2-hole excitation. We can keep these 2 slots filled, so the particles which occupy them. And then we have vacated the 3 and 4. And then we could have now 2 slots being filled here, so which is 7 and 8, and 5 and 6. So this will be an example of a 2-particle 2-hole state. So in order to set up the calculations which we want to do, we need now the following, and I'm going to call these for matrix elements. So phi 0 of H, this is a Hamiltonian. We've already calculated with a 1-particle 1-hole state, but we will also need to look at the 3-particle 3-hole state. So this is something which we know by default what it should be, right? Because we have only a 2-body interaction. So this is our famous roundest number, which we can think of, 0. And then we have the phi 0 of H and phi I, J, K, L, which is our 4-particle 4-hole state, A, B, C, D. And that has also to be equal to 0 because we have only a 2-particle interaction. So let's take a small break now. But what we can do now when we set up the Condon-Slater rule is that you can think of setting up blocks now. So you have a 0-particle 0-hole block. You have a 1-particle 1-hole block, a 2-particle 2-hole block, 3-particle 3-hole, and 4-particle 4-hole. That's the most excitations which we can make. And then when we link these, we know that this matrix element, an X, means that this is different from 0. I have a 1-particle 1-hole. I have a 2-particle 2-hole block. I have more than one configuration here because I can make many more 1-particle 1-hole excitations. If you look at the combinatorics, you can easily find out how many such 1-particle hole configurations you can make, and how many 2-particle 2-hole and 3-particle 3-hole. So that means that there will be more than one Slater determinant here, more than one here, more than one here, and here there's only one. So when you now are setting up this scheme, this is actually very useful because when you set up the Hamiltonian matrix and diagonalize, it's going to look like this. Because you're going to take the overlap between these different Slater determinants, which are your computational basis states. So in this case, this is non-zero. This is non-zero because I can connect a 0-particle hole with a 2-particle 2-hole, but this has to be 0 and this has to be 0. So what you will see now is that your matrix, if you now have 100 1-particle 1-hole states, this is going to be a very sparse matrix. In this case, it's going to be a little bit denser because we have only up to 4-particle 4-hole excitations. And you see now I can link a 1-particle 1-hole with a 2-body interaction. I can link that with a 3-particle 3-hole. That is possible. But I cannot link that with a 4-particle 4-hole, because then you will have 3 single particle states which differ from one determinant to the other. And then you see that this one has to be non-zero. In this case here, this is non-zero. But then this would continue like this, and this would be non-zero elements. And what you see now, if you're setting this up as a matrix, is that you will have a band diagonal matrix. So you will have a band with matrix elements which are non-diagonal. No, sorry, non-zero. And here, in this specific slot, which you see here, you have more than one contribution because you have many 2-particle 2-hole states. What we are going to assume is that the ground state is non-degenerate, which means that there is a unique representation of a 0-particle 0-hole. If we can have degenerate ground states, which is often the case in atomic physics, but we are assuming now that, so this would just give us one matrix element. If I have 10 single 1-particle 1-hole states, I'm going to have 10 matrix elements here, etc., etc. And you see now, if I do 100-particle hole excitations, there will be many zeros out here. And the matrix will be what we call a sparse matrix. This is the basic structure which we are going to explore now when we do full configuration interaction theory, which will be our first many-body methods. So if we can set up these matrix elements, then we can set up this matrix. Diagonalizing that one, we have all the eigenstates. Does that sound plausible, reasonable? Any questions? Okay, should we take a small break? Is that okay? Let's do let's meet at the 11:20. Is that, if that's okay, yeah? Now, with all these kind of things which we have, we can now start thinking on how we want to set up our first many-body theory. So what we're going to do now is to motivate the introduction of full configuration interaction theory. So every way we are going to distribute these single particles in different single particle states is going to be named a configuration. So you can think of this as one way to configure the system. This is another way, and that becomes a specific configuration. And then we are going to set up a Hamiltonian matrix defined by the basis of Slater determinants, which represent these different configurations. And then since we have an interaction, these configurations are going to interact. And that's why this is called configuration interaction theory. That's the reason for the name. And full configuration interaction theory means that we are going to set up a matrix which contains all the possible configurations, all the possible ways you can distribute a given number of fermions. And that's why it's called full configuration interaction theory. So let's just set up this. So this is going to be labeled FCI, full configuration interaction theory. And normally it's called FCI theory, but we're going to drop theory. So we just call it FCI. It's a method. So if we now look at a given state, we are going to make an assumption now that we have a basis of Slater determinants of SDs. And this basis is so set up. So this lambda can be one given 1-particle hole state, 2-particle 2-hole, etc., etc. So this lambda is just an index for a specific state. And this basis is so set up, and we're going to have an exercise. We are going to demonstrate that the Slater determinant basis, if we have a basis of single particle states which are orthogonal, which make this basis, then the basis of Slater determinants is also going to be orthogonal. So this is now defined in terms of this Kronecker delta. And this is going to be an exercise next week. And then we have a given state can now be expanded in this orthonormal basis. So expand the state. And we're going to call this a psi of I. And this state is the state which we are going to use as the state, which is an eigenstate of the full Hamiltonian. And that eigenstate is now going to be a linear combination of these basis states which we've chosen. And in principle, this runs from 0 to infinity. And then we have this basis of Slater determinants. We would have the same for the single particle basis. Now, I'm going to skip this infinity sign, and I'm just going to write this with the subscript lambda here, because we will always have to truncate this summation here. We can never run with an infinite basis. In the previous case, which we looked at for this Lipkin model with 4 particles, we end up with 70 Slater determinants when we do the combinatorics with replacement. And this is something we will rewrite now as a C of I. So this I can be the ground state of the system, or it can be any state of those 70 states. So when we are going to diagonalize the Hamiltonian matrix, the coefficients we get when we diagonalize, the eigenvectors are actually these coefficients. That's what we will obtain from the diagonalization problem. And I'm going to go through these details now, just to remind you of these technicalities, which you may have seen when you took a course in linear algebra. And this now gives us a sum over lambda equal 1 to infinity in principle, and then I have a Ci lambda. So I'm singling out the ground state here, and the hope is obviously that this ground state, ansatz which we have here, this is our reference vacuum, by the way. This ansatz, the hope is always that this contains most of the information, and that what comes from here is just a tiny contribution to the ground state wave function. Okay, so this is probably something which you've seen many, many times before. Now, I'm going to reorganize this sum now in a specific way. And we will reorganize the sum, which I put up here, this lambda of Ci lambda, in terms of particle hole excitations. This is just a way to reorganize the Slater determinants in terms of particle hole. I write this as a pH excitations. So that means that I'm going to write now, and let us now focus on the ground state, but it could be any state. So we are now going to look at psi 0, but as I said, this could be any of these states which we would get if we diagonalize the Hamiltonian matrix. So this psi 0 is something which we can write out now in terms of a C0. I'm just skipping the subscript 0 here. So I'm just going to mainly focus on the ground state calculations. But when you diagonalize, you get all eigenstates and all eigenvalues. So this is going to be given by phi 0. And then my first contribution here is a sum over one particle, one hole Slater determinants. And I'm going to write these coefficients in this specific way. And that's going to contain the one particle, one hole excitations. So that's one set of excitations. Then the next term which we get is going to be a sum over A, B, I, J. This is going to be the two particle, two hole excitations. And this has now a state of Ij of AB. And this goes all the way up to N particle, N hole excitations. I'm just going to write it like that, the final one. So this term here would be a one particle, one hole. This is obviously a two particle, two hole. And then we get three particle, three hole, etc., etc. The thing which is interesting for us now is that we can rewrite everything in terms of the vacuum state which we have chosen. the reference vacuum state. And to see that, we can now bring in the creation and annihilation operators. So the first term is going to be given by AI of Ci of A, and then I have A dagger, AI, and that's acting on phi 0. And then I have plus, and then I have AB, IJ, and then I have my CIJ, AB, and then I have my AI, AB, AJ, AI of phi 0. And this continues all the way up to n particle, n hole. So when we do that, you see now that we can actually rewrite. Let me just bring it back here in case you haven't written it. When you look at these expressions, we can then single out phi 0. So it's common now in many body physics to redefine this as a constant C0 plus an operator C hat, which I'm going to define now, which then acts on the ground state. This way of writing out a given wave function is not limited to the ground state only. I could actually do that with excited states as well. So I could target the ground state, or in this specific case here, you see that here I just put phi 0, but the coefficients could be the coefficients which relate to any other state. And what I have then is, if I look at this specific operator C, this is now going to be given by a sum over AI. I have a CIA and an A dagger, AI. This is all I always mess up when I have AIs and J's and so on. And then plus plus, and up to the n particle, n hole operator. So we would typically rewrite this in a more compact way now. So we can write this out. The state, psi 0, can be written out as a sum. And now I'm writing this as a pH here. This is a generic particle hole excitation. It can be 0 particle hole. It can be 1 particle, 1 hole, 2 particles. So this is a kind of generic notation now, where I just write this CHP, and this is acting on phi HP. And as you saw, we can rewrite this now as a particle hole, and then I have this coefficient CHP, and then I have the set of creation and annihilation operators. If I have a 2 particle, 2 hole, it's going to be given by these 4 guys. That will be this operator. If I have a 1 particle, 1 hole, then this operator is given by that one, etc., etc. That sound reasonable? These are just redefinitions. And then I have, I multiply this term here with phi 0. So in case, if you look at this one, if I have a 1 particle, 1 hole, then this A of H of P is equal to an AA and AI, like that. And then we can continue along this line here. So one thing which is very common to do now when you do many body physics is to use something which sounds a little bit odd in the beginning, and it's called intermediate normalization. And I'm going to explain how that is used, because when you now look at these coefficients which we have, what we are going to assume, obviously, is that when we normalize the state, psi 0, this state, when we normalize it, then we have a CHP squared, which has to sum to 1. That's a normalization condition. So you can see that when I take now a psi 0 with itself, psi 0, that has obviously to be given by the sum over all these particle hole configurations, pH prime, and then I would have my CHP complex conjugate times CHP. And then I have all these operators. So I have the states where I have now a phi of HP. So this is prime, prime. And this is multiplied with phi of H prime of P prime. So we're assuming that this is an orthogonal basis. And that simply reduces to the sum of a P of H. And then I have my CHP squared. Because I have assumed that the basis is an orthogonalized basis, an orthogonal basis. Now, there's something which is common to use in many body physics, and it's called intermediate normalization. I never liked this stuff, actually. It always confuses people in the beginning. But when you look at this sum here, since this sum has to be equal to 1, you could define now the overlap between phi 0 and psi 0, which is given by this coefficient C0. You can define that one to be equal to 1. That means that what you're doing now is that you're reshuffling the weight into these different coefficients. So this is normally called intermediate normalization. And that is simply because then you want to simplify this wave function, psi 0, and you rewrite it like 1 plus this operator, which now contains all the informations about correlations with the other states. And this will be given by phi 0. This operator C hat is called the correlation operator because it brings in correlations between different states. And depending on how strong these correlations are, if you look at the sums which we have here, if now a one particle, one hole excitation is what is the most relevant and most important type of excitation, then the hope is that these type of correlations or excitations and higher ones play a negligible role. So you could perhaps then approximate your wave function with one particle, one hole excitation. If a Hartree-Fock basis is a good basis, this is actually what happens. We are coming back to that. However, many of the interactions can be pretty strong. And that means that you will bring in terms of a two-particle, two-hole, three-particle, three-hole, etc., etc. And if you go to systems like nuclear physics, you can actually have a four-particle, four-hole excitations which are dominant in specific nuclei because you can form alpha particle excitations in oxygen-16, for instance. So oxygen-16 can be thought of as a composed of 4 alpha particles. And one can actually see that experimentally, that there can be 4 alpha particle excitations. So you have states which are dominated by that, and that's it's 2 neutrons and 2 protons. And that is something you can define in terms of a 4-particle, 4-hole excitation. And that means that higher terms here become important in your many-body description. Now, at the heart of all of many-body physics, all the many-body methods, every method we're going to discuss, whether you do stochastic methods, Monte Carlo methods, etc., deal with one way or the other ones of finding these guys here. When you diagonalize, these guys are going to be the coefficients of the eigenvectors. When you do many-body perturbation theory, you're going to do a Taylor expansion in order to obtain these parameters. And there are many different ways of obtaining them. When you do Hartree-Fock theory, you're actually neglecting all these terms. And the Hartree-Fock calculation is actually going to give you these guys. And so on. So different many-body methods are actually approximating the way you try to obtain information about these coefficients. And that's why I say when you can diagonalize, if you can diagonalize the problem, you will get all these coefficients and you solve the problem. But as you've seen, even in this small case with the Lipkin model, which we discussed here, you have something like 70 states. So your matrix to diagonalize is going to be a 70 by 70 matrix. But as soon as this number here grows, and in principle, this number, which you see here, the number of single particle states is infinite. That means that the dimensionality will just explode. And there's a limit to how big systems, how many degrees of freedom you can include in a diagonalization approach, which is full configuration interaction theory. But if you can do it, then you have the exact answer, or the exact answer within that effective Hilbert space. That's a more correct statement. Okay, so let's now look at the definition of the expectation value. So if I now look at my Hamiltonian and want to calculate the expectation value of the energy, what I would do then is simply to set up the standard definitions for the expectation value. And this is now going to be the ground state. When I write E0, we are targeting the ground state. But there's nothing which hinders us to get the other states when we diagonalize. And this is given by what's in, if you remember from linear algebra, it's called the Rayleigh-Ritz coefficient. So in this particular case, what we're actually calculating is this quantity here, psi 0, divided by the norm. So you can think of E0 as a Lagrangian multiplier. You can multiply away the denominator, and then we want to optimize a problem where we have the expectation value here, and E0, which is a Lagrangian multiplier, multiplied with this constraint here, which we want to normalize the one. So let's just look at these expressions here, because when we have E0, or if we multiply away the denominator here, what we get then is a function which we want to optimize, which is going to be a function of these particle hole excitations. And this is going to be given by phi 0 of h of phi 0 and minus of E0 multiplied with phi 0 of phi 0. And now I'm going to write it out in terms of these coefficients. So what I will get then is a double sum over P and H. And then I have a PH prime. And then I have my coefficient of C of H of P complex conjugate. And then I have my C of H prime of P prime. And then I have my Hamiltonian. So I have a phi of H of P. So this is just a generic particle hole excitation. I have my Hamiltonian, and then I have a phi of H prime of P prime. And this is minus the term which now runs like a double sum of P of H prime. And then I have C of HP, complex conjugate again, C of HP. And then I have my term, E0. And then I have these overlaps of H of P. And we know that these states are orthogonal to each other. So that is just going to reduce to a single sum of a P and H. So what I'm going to do now is to optimize this term with respect to the complex conjugate, CHP. And you can actually show that this is a sufficient condition to optimize with respect to one of them. They are not going to be coupled equations, so it's sufficient to look at one of these. And what we get then, when we require that this has to be equal to 0, so we are optimizing this one, so rather minimizing it. And we want to drive this to 0, because this is essentially what we are trying to find the solution of to that problem. I guess you're familiar with this kind of Lagrangian formalism with Lagrange multipliers and so on. And what we end up with then when we optimize this and take the derivative with respect to the complex conjugate ones is that we have a PH prime, and then I'm getting a term of phi HP of H phi of H prime P prime. I have the coefficients CH prime of P prime minus, and then I have my E0 of CH prime of P. And this is a quantity we want to be 0. Now, what I'm going to do now is just to make things a little bit more compact. I'm going to change this summation of a P prime and H prime into just one index. So I'm going to change that to a summation of a J. So J stands now for a particle hole excitation of the one particle one hole type, two particle two hole, etc., etc. So I'm also going now to rewrite some of these terms, like this term here, P of H prime of P prime. That's going to be given by a overlap of phi j. And this is given by an overlap integral. And normally we are going to put this one equal to delta ij. That's the basic assumption we are going to deal with. We are going to assume that the basis is an orthogonal basis. If not, you need to calculate this overlap. If we use that and then introduce another notation, I'm going to rewrite now this Hamiltonian. Now this is expectation value of transition from one state to the other one via the Hamiltonian operator. I'm going to write this out as something which will lend itself for a matrix notation. So I will simply call this an Hij. I just want to compactify the expressions which you see here. And if I do that, then we are getting the following expressions. If we also now, is it okay if I change page? So I'm going to relabel CHP as a C of I, and then the CH prime of P prime as a CJ here. And then I can rewrite the equation which you saw on the previous page. You can then rewrite the previous equation as what we get then is a sum over J instead of P prime and H prime. I'm getting CJ here, and I have my Hij minus this E0 multiplied with this Sij, and we want this to be 0. And we know that that problem has a solution if the determinant of H minus E0 times this S is equal to 0. So we know that this has a solution. So this is a typical homogeneous set of equations which have a solution when the determinant of the coefficients are 0. So that means if determinant of H minus this E0 times S is equal to 0. So that leads to the standard eigenvalue problem. So what we will have in basically all the applications which we are going to do is that we will have that this Sij is just equal to a Kronecker delta. And that means that if I plug that one into the equation, I get the standard equation which you may have seen in textbooks in quantum mechanics. And that standard equation is now given by this familiar eigenvalue problem, where you have the eigenvectors, and that's multiplied with the matrix elements, and that's equal to some eigenvalue, which in our case is E0, but it could be just a generic lambda, multiplied with C of I, where C of I is a specific eigenvector. So I guess these are things you have seen a little bit here and there in linear algebra and also in the basic quantum mechanics course. So this is essentially what you have here is actually the FCI equations. And let's just mark this. This is the basic FCI problem. So these are the FCI equations to solve. And if you can diagonalize this, then you have the solution. And then you will get all eigenvectors and all eigenstates. Sorry, all eigenstates mean all eigenvectors and eigenvalues. So in our case now, we have defined the Hamiltonian. This is going to be something we will label as the Hamiltonian matrix. And that will contain all these overlap integrals, which we have discussed. And if we now take a closer look, so we can rewrite also this problem here in a more generic way as a matrix H times a vector C, and that's given by a eigenvector lambda multiplied with a vector C. Does that sound reasonable? The way we came here? Maybe I should rewrite it a little bit. So the way you can think of this now, suppose you're looking at the ground state of the system, this specific case here. So let's try to rewrite this in terms of a given Hamiltonian matrix. So what we have now are this given state, phi 0, and then we have this phi of IA, and we have a phi of ij, AB. So this would be the 0 particle, 0 Hall states, the 1 particle, 1 Hall states, the 2 particle, 2 Hall states. And this goes all the way up to n particle, n Hall states. N Hall. And then we have the similar block here. So we have a phi 0. We have phi IA. We have phi ij AB. And this goes all the way down to n particle, n Hall excitations. So what you have in here are the matrix elements. And this is then multiplied with these vectors, the vector components. So there will be a C0, there will be a CIA, a CIJ, AB, and this goes all the way down to C of n holes and n particles, like that. And in here, you have matrix elements, and some of them are 0 if you have a two-body interaction, so there will be zeros up here. And if you have a two-body interaction, these will be 0, and these will be non-zero, and then I will have zeros down here, etc. So it's going to be a band diagonal matrix like this, and this is going to be equal to the eigenvector multiplied with the eigenvalue. So the eigenvectors you find now by solving the problem are actually these coefficients. So that's why when you if you can set up the Hamiltonian matrix, then you diagonalize in that basis you have, and then the eigenvectors give you these coefficients which we discussed here. These specific coefficients is what you get from diagonalizing. And when you have these coefficients, that means that you can go back and calculate, for instance, the expectation value of the energy. So just to end with one small thing, if we look at the first row here, this specific row, so now we multiply from the left with phi 0, and we multiply with the Hamiltonian and this linear combination. So if you take phi 0 and multiply with these elements you have here and the vector, so that's the first row. So that means that we get phi 0, and we multiply that with h minus, and I'm now shifting over to the left, this E0, and this is multiplied with psi 0, and we want this one to be 0. So if I do that, what I'm going to get now is phi 0 of h, and when minus E0, and then I have this sum which has a coefficient which I now put to 1, so I have phi 0 plus this A of I of CIA multiplied with phi IA, and I get the higher order terms A, B, I, J, C, I, J, A, B, phi I, J, A, B, and this goes up all the way up to n particle, n hole. So now I'm just taking the first row which you have here, this one, and multiplying everything here with phi 0. And then I'm subtracting what I have on the right-hand side. So I'm subtracting this piece here. So what we get then when we do the algebra, and this is where we're going to stop today. So if you look at the first term, that is nothing but the reference energy. So I'm going to get phi 0. And then I have my reference energy with H of phi 0. This is my reference energy, E0 ref. I get minus E0 multiplied with phi 0 and phi 0. And in this specific case, we know that we have a two-body interaction, so we cannot get more than a zero particle, zero hole, which connects with a two particle, two hole excitation. So what I will be getting, and this is where we will stop now, I will have a sum over AI. I have my phi 0, which is being multiplied, and I have my H, because E0 is just a constant, and the state's orthogonal. So that means I'm getting phi IA, this one, multiplied with CIA. And this is something which we have calculated earlier. We know the value for that one. These are the expressions which we started with in the previous lecture. And then the next one, which we are going to get, and this is the only non-zero one, is going to be phi 0 with a Hamiltonian multiplied with phi ij AB and Cij AB. Now, this expression contains much more information than meets the eye. So this actually lays the basis for many of the many-body methods which are going to come. So when we are doing many-body perturbation theory, we will make an approximation to this. The same with copper cluster theory. If we use Green's functional theory, any many-body method implies an approximation to these coefficients. When you diagonalize, this is what comes out of your diagonalization method. And then you could actually recalculate this E0, but you don't need to do that because you get it from the diagonalization. But what is interesting now is that you can single out the difference between E0 and this reference energy in terms of these two contributions. And that's going to be called the correlation energy. So this difference, E0 minus E ref, because this equation here is actually has to be equal to 0. So I would shuffle E0 over to the right-hand side and subtract the reference energy, and that gives me the correlation energy. That would be the contribution to the energy beyond the reference energy. So you have a measure for what comes beyond the ansatz you have made. And that's extremely useful because then you can interpret your results in terms of excitations outside of the vacuum reference states which you have chosen. And then you can go back and you can say, okay, my Hamiltonian is a specific type, and it gives rise to important one particle, one hole excitations, whereas these are perhaps small. When we are going to run a Hartree-Fock calculation, these guys here will be 0, and the only term which comes in is here. So I'm going to show you this again and again because it forms the starting point for different many-body methods. So different many-body methods imply approximations to the way you obtain these coefficients. As it stands now, if you can calculate, diagonalize, then you have the answer here. And then you know what these coefficients are. We stop here. Is that okay with everybody? We're actually over time.